In the last video, we defined heat as an energy transfer. It's an energy transfer between a hot object and a cold object. The hot object has more molecular kinetic energy. Its molecules are moving faster. They collide with the slow-moving molecules in the cold object. And you'll have two heats. A Q hot for the hot object and a Q cold for the cold object. And you'll have two temperatures too. There'll initially be a hot temperature and a cold temperature, and there'll be a final temperature. After the heat is done flowing, the temperature of the two objects will be the same. So I'm going to use these symbols when we're talking about problems here that have to do with relating temperature differences to heat. And I'll always use a Q for heat. Temperature differences, we're going to write down using the symbol delta T. So this is one symbol. The delta means a change in. So this is a change in temperature. And it's defined like this. It's the final temperature minus the initial temperature. So in my picture right here, if I want to look at what Q hot is, I want to relate that somehow to the temperature change. And the T initial here will be what the Q hot, what the T hot was originally. Now, what does this equation look like? It turns out to be as simple as possible. You just put a constant there and it works. This is called a direct proportionality, in that if you double the temperature difference, you're going to double the amount of heat that flows out of the hot object. And this constant is a constant of proportionality. So that's a constant. This is the heat flow in and out of the hot object. Now, does energy leave the hot object or go in? Well, we know from what I said up here that energy transfer always spontaneously occurs from the hot object to the cold object. So the heat is always going to be leaving the hot object. So it's always going to be a flow out. But we're going to have a way of tagging that, which we'll see in a minute. This constant is called the heat capacity. It is the heat absorbed by the object per 1 degree of temperature rise. Now, this always has to be a positive number. How come? Well, when you heat something, when you pump heat into it, the temperature has to rise. So you can't heat something up and have it get colder, have the temperature drop. And for that to happen, Q hot and delta T have to have the same sign. And for that to happen, you've always got to have a positive heat capacity. This is kind of a sanity check on your results. If you're getting negative results for a heat capacity in your calculations, you missed a sign somewhere. And here's the temperature change. And it's going to be the final temperature that we've talked about over here, minus the initial temperature of the hot object in this particular case. Now, let's put a box around that. You know at this point in the course what that means. Now, this equation would, you could have another equation that would apply to the cold object. Its heat capacity might be different. This heat capacity is in general going to be different for every object. Suppose I've got a situation like this. I've got a hot object. Let's say some coffee. Let's say now notice the units that I put on the heat capacity in this problem. Heat capacity is heat absorbed, which is in joules per 1 degree Celsius. So the units are going to be energy units divided by temperature units. And that's just what we have here. How much heat? Was absorbed. Okay, well, you can pretty much just plug into this equation here. This is Q for the coffee. It's going to be C for the coffee times the temperature change for the coffee. They give us C for the coffee. And the final temperature is 39 degrees. And the initial temperature is 9 degrees. So the temperature has risen, and you're going to see a positive sign on this. So this thing is going to be not just 30 is the difference, but plus 30. It went up by 30 degrees. Okay? So we got 30 times that, that's going to be 1200 and some change, right? 1240, 1250, something like that. You just multiply this times 30 and you'll have it. What I want you to notice, say it's like about roughly, I don't know, 1250 or something. Because it'll be 30 times that. Now, let's see. What I want to point out about this is that you've got a positive sign on this. And that has some meaning. When you've got a sign on your temperature difference, your temperature change could be positive, which means that the temperature rose. That means that T final was bigger than T initial. And negative means that the temperature dropped. So the sign means something with a delta T, and you've got to get it right. It's important to put the final minus the initial and not the other way around to get the sign right. But whatever sign this is going to be, since this is always positive, this will also have a sign. And if it turns out to be a positive number, it means that heat was absorbed. Something from the surroundings caused heat to come into this. And if it was negative, that would mean heat was released. So we can say, oh, roughly 12,500 joules of heat were absorbed here for this, roughly. I just rounded this off in my head. Pick up your calculator and get the right answer. Should be somewhere in that ballpark, right? Okay, so we can use this equation to, if I give you any two of these things in this equation, you can find the third thing. On your worksheet, you've got a problem where you're trying to find what the heat capacity is, given the Q and given the delta T. Now, you can also see this equation in a different form. If you know the mass of the object, and the object is made out of one material, there's something else you can do to solve this problem. If you don't know the mass, like we didn't know the mass of the coffee in that last problem, you'll have to use this. But if you do, what we can do is, instead of using the heat capacity, we can use a heat capacity per gram. This is called the specific heat capacity. And sometimes, a lot of times in engineering, they will use the word specific to mean per gram. So whenever you see specific, it means per gram. And this is the mass. Now if you multiply the mass times the heat capacity per gram divided by grams, the grams cancel out and you get this first equation here. But this is a lot more useful when you know the mass, because you can actually look up in tables what the specific heat capacities for different materials are. For example, the specific heat capacity for water is 4.18 joules per gram degree Celsius. Now notice that joules per degree Celsius is the unit for heat capacity, and joules per degree Celsius per gram is the unit for specific heat capacity. For copper, S is a different number, something like 0.3 joules per gram degree Celsius, something around that. Water has a much, much higher specific heat capacity than copper does. And what this means is that you have to heat water a lot more. You have to pump a lot more heat into water to see its temperature go up. Imagine putting like an empty copper pot on top of the stove. It'll get very hot very fast. And if you put a pot with water in it on the same burner, in the same amount of time, it won't get nearly as hot. You know, the temperature won't rise nearly as much. There are some substances that can absorb a whole lot of heat without you seeing a big temperature rise. And there's some substances where you can't. Metals usually have very low specific heat capacities. Water has an unusually high specific heat capacity. So now you have two tools, this one or this one. Whenever you have a problem that asks you to relate a temperature change with a heat, you can use one or the other. And in this problem, I could give you any, there's four things there, right? I could give you any three of those things and ask for the fourth one. And when you do the homework 6, you're going to see that there are a whole lot of problems that are just like that. Let's do just one, and then we'll go on and see what happens when we have more than one object involved in a problem. Suppose I have my coffee and I say it has the same specific heat capacity, and sometimes people say just specific heat, not specific heat capacity, but specific heat capacity as water. This is true in general of a lot of solutions. It's very close. The solution is mostly water, so it will have a specific heat capacity pretty close to the value that I gave you there. Now, let's suppose that the coffee is placed in a microwave and absorbs, I don't know, 100,000 joules. Suppose I have a, let me see, my coffee cup is about 300 milliliters. So suppose I have 300 grams of coffee. If it starts at room temperature, (25°C), what's the final temperature? All right. Now this looks like a complicated problem. There are a lot of numbers in there, but what you have to realize is that you're trying to relate a temperature change to an amount of heat. And in that case, you're going to pick one of your two tools here for doing that. And since I do know the mass of the coffee, and it talks about the specific heat, this is the one that I'm going to use. So now I have Q equals ms delta T. Delta T is going to be the final temperature, which is what I'm really trying to find in this problem, minus the initial temperature, which was 25°C. The specific capacity of the coffee is the same as for the water, so I can write that in as 4.18 joules per gram degree Celsius. And the mass is given, it's 300 grams. So I'd take 300 times 4.18, that's like about 1200, right? Times T final minus 25 degrees. Now I've got over here 100,000 joules. So I've taken Q equals ms delta T and I put the numbers in wherever I could. Now what I want to do is solve this equation for T final. So it's not a chemistry problem after this point. It is pretty much just an algebra 2 problem. We have to get T final all by itself, so we have to get it out of these parentheses. So what I'm going to do is divide both sides by these numbers. Oh, and by the way, I said absorbs, so I know that this is positive over here. I know what the sign is on it. So I can divide 300 grams and 4.184, well, I'm going to just say 4.18 because that's what I've been telling you. That's equal to T final minus 25°C. So to get rid of the 25°C on this side, I can just add it to both sides. And there is my final temperature. It's going to be higher than 25 degrees. The amount that it's going to be higher is this. So it's going to be 100,000 divided by about 1,200, whatever that is going to be. And you can figure out the final temperature from that. Now in all of these problems, we're only talking about one object. Like in this problem, we're talking about the coffee, but we didn't mention the cup that it's in. The cup might get warmer or cooler in a problem too. In the next video, we'll talk about problems that have more than one object, which is the type of problem that you're facing at the end of the worksheet.